Okay, welcome to the fifth class in the Origin and Evolution of the Moon class. My name is Jim Head at Brown University, and together with David Kring at the Lunar and Planetary Institute, we're co-sponsoring this course. The really important news this week, in addition to this class, of course, is that NASA has submitted to Congress a report that was due from Congress actually last year, but I encourage you to take a look at it. We'll post it online here. This outlines the plans for NASA for future human exploration, and it's, to me, quite good news in the sense that there's a lot of indications about beyond the gateway, in fact, very closely associated with the gateway, in the sense that it talks a lot about returning humans for exploration of the moon in the short term, and building landing craft to land humans on the surface as well as part of NASA's program itself. And so the combination of human and robotic exploration really bodes well for our future understanding of the moon. And I just wanted to point it out again that on November 7th, NASA Administrator Jim Bridenstine will talk to us. I've checked in with the Chief Scientist, Jim Green, and that's still on schedule. He's going to do it live. And so we'll have a great question and answer period after that as well. NASA Administrator Bridenstine is also, I think, today testifying at Congress, and so we'll hear a lot about these plans in the very near future. So next week we're going to hear from Maria Zuber, who will talk to us about the structure of the lunar crust, mantle, and core. And as you know, Maria was a PI on the GRAIL mission, which brought huge insights into our understanding of the nature of the crust of the moon, its thickness and characteristics, as well as implications for the deeper interior. Today we're really lucky to have with us Marc Parmentier here at Brown, who is going to talk to us on the formation of the lunar crust and the aftermath, the magma ocean hypothesis. Marc received his BS in engineering and mathematics at West Virginia University, went on to get a master's in engineering and PhD in geophysics in 1975, both from Cornell University, and then did a postdoc at Oxford University. He came to Brown in 1977, and he's been with us here ever since. And Marc provides incredible insight into mantle convection patterns, origin and evolution of layering in planets, and many other aspects of the dynamics of planetary evolution. So today, again, Marc will talk to us about the formation of the lunar crust and the aftermath, and this will be nicely followed next week by Maria's discussion of aspects of the structure of the lunar crust, mantle, and core. So let me turn it over now to Marc. Marc? Slide on there. You're on.
Okay, great. Well, it's really nice to have the opportunity to join the class today. I understand from talking with a number of you that it's really been an exciting experience. So the broad title of my talk today, as I have entitled at least, is The Dynamics of Lunar Mantle Evolution, Exploring the Role of Compositional Buoyancy. And this is actually quite similar to Jim's title, which he gave you earlier, but it really just reflects a slight difference in perspective, which is good, because one of the things that we want to do, and which I think you're probably doing in this class, is hearing about lunar evolution from a variety of perspectives. So that's good. So at any rate, so where do we start? Well, first of all, my goal, I'm going to assume that you've all, there were a number of papers for reading, and I'm going to assume that you've all read the papers in the journal called Elements. These are going to provide, they're really short, usually to the point, and they'll provide you with some pretty good background for what I'm going to talk about. I'm not going to try to redo those papers. Rather, I'm going to try to take, after a brief reminder of what I think you may have read about, should have read about in those papers, then I'm going to try to tell you how that kind of information might be useful for thinking about the dynamics of lunar mantle evolution. We're going to talk a lot about models today. I think you should be clear that models and the models that I'll show you at least from my perspective, are not intended as simulations of the moon. Models are tools that we use, much like you'd use laboratory instruments to make observations. Models are based on a set of assumptions, and the role of the model is basically like a function. You put some assumptions into the model, and out from the model comes, some quote prediction. So I think, I think with that caution, and I hope we can go forward, and hope, don't hesitate. The other side of that is that don't hesitate to question models, right? You should question models. That's what we have. That's what we have models for, to help us formulate questions in new and different ways. Okay. So anyway, that's some generalities. Also here, what I tried to do as much as I can in this talk is really stick with stick with pretty contemporaneous work. I'll try not to go back and tell you too much about history. Have to talk a little bit about history. And so, one piece of history is the existence of the lunar crust and the discovery that, it's made predominantly the north side. And it's pretty remarkable that John Wood, who was involved in the early Apollo program, deduced the idea that one good way you could produce this lunar crust was with the magma ocean. And so the magma ocean hypothesis was basically born, I suppose. And it has survived for a long time. And so people like me come along 20 years later and try to understand how magma oceans might work. And one way you can understand how magma oceans might work is by first of all, looking a little bit about how the moon has evolved. In other words, first of all, what was the aftermath of the lunar magma ocean? And if the lunar magma ocean created a certain, quote, initial lunar structure after it solidified, and it should have solidified pretty quickly within a few hundred million years. What can we see in the next 4.4 billion years of lunar evolution that would begin to tell us something about what that initial structure might have looked like? So the first section of the things that I'm going to talk with you about are really studies that sort of look at the question of sort of, in some sense, the geologic evolution of the moon and how that might be tied to the internal dynamics. So here we go. So first of all, what do we know about the moon? We know a lot about the moon. This is my own list of what we know about the moon. There's the pointer. And so actually we know quite a lot about the moon. First of all, we know there's a strong hemispheric crustal asymmetry. Again, I don't know how much of this you guys have already talked about. But so there crustal asymmetries. The other thing we know about them, oops, sorry, I did that wrong thing. Keep losing the pointer, there it is. Second thing we know from Apollo samples is something about the Mare basalts. We know something about their composition and how the Mare basalt composition is related to north-site. Under number 3, the second thing we know is something about the timing of Mare basalt emplacement and how the composition of Mare basalts evolved over time. We know a fair amount about the structure of the lunar mantle. I'll show you examples of these kinds of features. And finally, we know that the moon had an early core dynamo magnetic field, and somehow we need to find among the suite of models that we might consider viable candidates for how the moon looked after the magma ocean and how it evolved subsequently. Our models have to allow us to have to be consistent with the existence of a lunar dynamo field. Okay. So, you know, there are a lot of things that we know about the moon. Lots of things about the moon are not nearly as well sampled as they are for the Earth, if you're coming at this from an Earth perspective. But nevertheless, there are a lot, and we need a lot more, you know, we need a lot more study of the moon. You know, we need to increase the number of observations that we have so that all of these characteristics that we see here become even better founded, hopefully. Okay, so let's just go back. Mare basalt. So we had so the picture is we had this north acidic crust that formed early, formed because plagioclase, in some sense, floated in the magma ocean. What happened next? Well, what happened next is, in a geological perspective, is that Mare basalts were erupted. And a couple important things about the Mare basalts. First of all, the figure on the left here, on the right, actually, pointer's not so great, shows the Clementine titanium distribution. And so you can see the hemispheric asymmetry of the moon, okay, something that you've already read about. And you can see that the Mare basalt, the region that contains high titanium, is on the near side of the moon. Far side of the moon, the number of such Mare basalts is extremely limited. Second thing you can see is that if you look at the Mare basalts, composition of Mare basalts as returned from Apollo as a function of age, then you can see that the Mare basalts, whoops, sorry, here we go again. Essentially, if I tap it twice, yeah. Mare basalts essentially evolved from a high titanium composition to a low titanium composition. And that must be telling us something about what happened in the interior of the moon. And one of our goals is to think about how we might interpret that. Does
that correlate with iron content?
What?
High and low titanium.
Yeah. Mm-hmm. So, yeah, I could have shown you an iron map that would look, you know, look about the same. So, okay, so one of the Rosetta Stones of the lunar magma ocean, where is this thing? There it is shown in the diagram on the right, which in this case I've taken from a review paper by Paul Warren, which shows you the fractionation of trace elements. Excuse me for a minute. I don't know what's going on here. So one of the things you can see is that the north sites. You can see that the so-called European anomaly between the north sites, the north acidic crust, and the Mare basalt as this sort of complementary anomaly. And so the inference from very early on was that the Mare basalts were derived from a mantle source that was complementary, that is, was residual to the north acidic crust. And so you might have a picture of the north acidic crust forming, and then somewhere underneath that are all of the more mafic minerals that are left over when the magma was in place, when the north site was in place at the surface. So how deep? So we have Mare basalt magma, so that implies that there's been some melting. And so how deep did that melting have to occur? And one way we get at that is by looking at the most primitive of the Mare basalts that we think we can identify, and these are the sort of ultramafic lunar glasses. one of the things that you can do, one of the important things you can do with the lunar glasses is that you can ask at what depth the lunar glasses that we have from Apollo samples could be in chemical equilibrium with a mantle, a lunar mantle that contains both olivine and orthopyroxene as minerals. And that generates essentially a unique depth for each of these, for each type of glass. And you can see there are a range of glass types here. Okay, Pointer, come back, Pointer. Where are you? Oh, I'm sorry. You can see that, from the different colors, you can see there are a range of glass types. There's sort of the high titanium glasses, which probably correlate with the high titanium Maury basalts, and then there are the other lower titanium ones that in green. And so we can talk about the density, and in the Grove and Krasinski paper, they actually talk about the density. But the main point that I'd like to make here is that the implications of multiple saturation is that all these things come from depths that range from 300 to 500 kilometers in the moon. That's where the melting presumably took place that generated them. But yet we know that the North Acidic crust is sort of only 60 kilometers thick, and probably there was only 100 kilometers or so of mantle underneath that would have been residual to that crust. And so something must have happened if we have this residual mantle that we'll call creep for the sake of simplicity, that was initially at relatively shallow depths, like 60 kilometers, and it ended up melting at much greater depths, like 3 to 500 kilometers. That has to speak to the fact that there was some kind of mobility of material inside the moon. All right, and mobility of material inside the moon is kind of really the key to thinking about how the moon may have evolved. The other important feature that we have of the moon is something about the distribution of radioactivity within the moon. This is a map of the thorium concentration measured on the surface by lunar prospector. And you can see that high thorium concentration occurs on the near side in generally the same areas as the Maury basalt. And later on, we'll say that actually the thorium concentration actually appears to be, it has been argued that it's rather symmetric around the Imbrium impact basin. And we'll talk a little bit more about the potential implications of that later. But the important thing about thorium is that uranium, thorium, potassium, these are the major heat-producing elements in the moon that are going to control the temperature of the interior and how it evolves on 4 billion year timescales. And so the thorium is a good indicator of where those kinds of elements have ended up. And one of the questions that we're going to ask is if those kinds of elements were left behind in this sort of residual from forming in a North Acidic crust, where did they end up? Because it would make a big difference whether they stayed at shallow depth or whether they were in some way transported into the deeper interior of the moon. One of the most recent results that we have, the most recent results that we have about the moon, I think, come from the Grail mission, which you've all heard about. I think there's the paper by Marc that was one of the elements papers that you read, and there you can. I'll put a lot of references here, and if these are things that interest you, you should be able to find the papers if you want to read them from the information that I give you here. But basically, I think we have good knowledge about the crustal structure of the moon now, and Maria will talk about that more next week in much more detail than I'm intending to do here. We know about the crustal thickness. one of the points that's going to come up later, though, is that we've also learned something about the density of the crust, as mapped out here, and also something about the porosity of the crust. And it turns out that I think that the lunar crust is lower density and higher porosity than as inferred from the gravity data than anyone had expected beforehand. And I will tell you in a little while why that might be important. Okay, so looking to the inside of the moon, what can we see? Well, the diagram up there, we can't fill up the whole screen, can we? So they're a bit bigger. Too bad. Okay, sort of emphasizes some of the main features of the interior of the moon. First of all, as I'll tell you a little bit, we know that the moon has a core that's metallic. This is probably, although not everyone would agree, this is probably where the magnetic field, the core dynamo that generates the magnetic field, comes from. And I think we know for sure that some of the core is solid, the dark region in the middle, and there's a liquid region around that. The evidence is moderately indirect. It comes basically from seismology. We know that if we have a region that's liquid, that it will propagate P waves, but not S waves, right? And so, compressional waves. So the figure here comes from the Longyon paper, and it shows ray paths of earthquakes that were detected basically at by the Apollo seismometers, and this is kind of the Apollo seismic network, which I think you've probably heard about, and you've read the Elements paper anyway. But one of the things you can see, and should have already seen, is that there's a region near the middle of the moon, even based on this very, very tiny seismic network, that it appears that there's a region near the middle of the moon where you can propagate P waves, but you can't propagate S waves. Okay. And so I think that tells you almost immediately that you have some sort of a liquid region near the middle of the moon. Okay. The other important asymmetric feature about the moon is the existence of deep moonquakes, shown by the symbols here, the dots. And these are again, while the seismic coverage is far from complete, you can see that these are located predominantly on the near side of the moon, rather than being more uniformly distributed. And so that probably tells us something about the mantle of the moon. Finally, the diagram on the bottom at the left is a seismic structure of the moon, the most recent one that I know of, from the paper of Weber et al. And you can see that some of the major features that show up here are, again, a solid inner core, a fluid outer core, and even more importantly, for some of the things that we're going to say later, there's apparently a region of not metallic core material, but of rocky mantle material that is just outside of the core that seems to have particularly low seismic velocities. So I don't know. Are people looking at this on their screens, or are you trying to? Okay. So you can see that in the oops, sorry. No, I have so much trouble with the pointer here. Does anybody have hints or? No? Okay, here we go. There he is. No, that's good. No, I just went around doing something wrong. But here, if you look at this, the shear wave velocity and the P wave velocity, you can see the inferred existence of a low seismic velocity region near the bottom of the mantle. low seismic velocities would generally correlate either with very high density or very high density or very high temperatures. Okay. And so one of the recent results here is some information that comes from the GRAIL data. The seismology, of course, is all Apollo era work, subsequently analyzed Apollo data. But the GRAIL data tells us something about the density, the moment of inertia, and the so-called love number of the moon. And again, the GRAIL data is consistent with fluid, a solid inner core, fluid outer core, and this deep mantle zone of low seismic shear velocity. And so there are a variety of lines of evidence that suggest that this is the structure of the moon that that exists right now. And so one question is, how did the moon get that way? And if it's that way now, what are the implications for how it started? And so ultimately, we're going to want to talk about want to talk about the so-called initial condition for the geological evolution, which would be the ideas that would be related to how a magma ocean would solidify. So as you learned last week, I think, from Robin Knipp, the general view is that one way or another the moon formed in association with a large impact with the Earth. And most people think that the moon would have started out basically totally molten. I don't know, maybe there's room for argument there, but that seems to be a prevailing view, I think. And so, so if you had a body the size of the moon that was completely molten, it would cool off with time, of course. And as it cools off, what would happen is that it would crystallize. And initially, come on, come back, cursor. There we go. Feeling I'm doing something wrong, but okay. So in a totally molten moon, the moon is hot on the inside and cold on the outside, and so the moon would be convecting rather vigorously, and sort of fluid dynamical parameters that would describe the behavior of the magma ocean are actually a lot like the parameters that you would use for the Earth's atmosphere. Okay? It would be very, very vigorous. The viscosity of magma is pretty high compared to air, but on the other hand, the magma ocean is really deep. And so all things taken together, one would think that this was a very vigorously convecting body of liquid, and that what would happen as it cooled off is that you would begin to generate crystals due to cooling at the surface, and the first crystals that you would generate would be the mineral olivine, and that olivine would be dense compared to the liquid and would sink to the bottom in this sort of idealized view. And you can see that that process would continue. Whoops, back we go. Process, okay, would continue with the so-called cumulate mantle building up over time. Eventually, you'd start to see olivine and pyroxene coming into the mantle. Again, that process would continue, but then at some point we would start to generate, the magma would become saturated in aluminum, at which point aluminum is an important part of the mineral anorthite. And at that point, you would start, once you take out enough iron, magnesium, and silicon that you saturate the melt in aluminum, then you'll start generating anorthosite crystals, which will presumably will, because they're less dense than the magma, are in one way or another going to want to move towards the surface of the moon. And so the general idea is that the anorthositic crust, the anorthosite, will accumulate at the surface of the moon, and it's buoyant, so it just kind of sits up there. it doesn't participate in all the convective overturn that's happening inside the moon. It just sits on the top, and heat has to conduct through that layer. And because it's not convecting, heat conduction is a very slow process. And so what would happen is you develop this conductive lid is at the surface temperature, which is how the moon is losing heat by radiating into space. Surface temperature is going to fall dramatically. The rate of heat loss from the magma ocean is going to drop to very low values. And at that point, we'll talk about timescales later on, but at that point, the magma ocean is going to slowly crystallize over timescales of several 100 million years. And you'll generate a crust and mantle structure that would sort of look like the stratigraphic column shown here on the right. So after the moon crystallizes, the picture that we have is that this is an old diagram from a paper that I had the opportunity to work on with Paul Hess, in which we explored what the consequences might be of the dynamics of this sort of fractional crystallization of the moon. At the time, we were thinking that there was some primitive moon around, like some moon that didn't participate in the magma ocean, and it's certainly still a possibility. But one of the things we did was calculate the density. On the diagram on the left, we calculated the density of materials that would crystallize from the lunar magma ocean. And one of the things that you can see is that come on, one cursor, go back, please.
On the TV.
Is it? Oh, is that right? It is up here, but it's okay. I don't know why it's not on the screen. Now I see it on the screen. Huh?
Laser pointer?
No, I can't do that. Anyway, that's fine. So one of the things you can see is in the purple stuff, these are the olivine piercing cumulants. And so one of the things that happens as a magma ocean so-called fractionally crystallizes, that is, you keep dropping crystals out, as fast as they form, and they can't keep re-equilibrating chemically with the residual liquid, is that the early cumulants are very magnesium rich, and the later cumulants become progressively more iron rich because iron is less compatible in the olivine and pyroxene than the magnesium. And so you get this sort of upward enrichment in iron. And finally, when you get really near the end of the crystallization, way up at the top there, you can see that the density climbs way up. Okay. So that sort of density spike at the top would be what I will usually call ilmenite-bearing cumulates, or maybe in some very broad, generalized sense, we'll call that creep. Not precise terminology, but not too bad. One of the things you can see is that the stuff that's at the top of the magma ocean is really dense, and the stuff that's at the bottom is less dense. And the density variations that we see there are really quite large. The little horizontal dark bar that you see shows the amount of density change that you would have if you changed the temperature by 1,000 degrees centigrade, which is a big temperature change. And you can see that the density variations that come from the composition are large compared to temperature changes on the order of 1,000 degrees. So they're large. All right. It's also true that most of the heat production of the magma ocean is going to end up in this little spike of material at the top in the ilmenite-bearing cumulants. Okay? So where they go is going to determine where the heating, the radioactive heating, occurs within the moon. So one simple thing that you could do, which is what Paul Hess and I did, was to simply take the stratigraphy that you see on the left in terms of density and simply rearrange it so that densest material was at the bottom and the least dense material was at the top. And so, as you might imagine, that little high peak of very dense material ends up down here, ilmenite-bearing cumulus. Looks a lot bigger at the bottom than it did on the top, but that's because the moon is a sphere, right? So you take a thin shell, near the surface of the moon, you put it deep, and it looks a lot thicker. And the other thing that would be true, so what we should end up with afterwards, if this were the way the moon worked, or the way the moon worked following the solidification of the magma ocean, is that you would end up with very dense heat-producing elements at the bottom, the ilmenite-bearing cumulus. You would end up with the olivine and pyroxene cumulus sitting above that, and they would generally decrease in density as you went up. And finally, on top of that whole package, you would have the North Pacific crust. And if you had primitive moon, it would end up sandwiched somewhere in between the cumulus. So that's a very idealized picture of, and I'll show you some more realistic, perhaps, attempts to talk about overturn later. But as a first shot, lots of people have looked at the idea that the picture that you see on the right there is in some way representative of how the moon looked in terms of density and composition just after the magma ocean crystallized and overturned. Right? So, this is a model. Again, it was a study that I had the opportunity to work on as well. And the model started with the chemical structure of the moon that's just like we described just a minute ago. It's going to be a spherical model. And on the left, you can see that we're going to say that we have these ilmenite-bearing cumulus in red. We have a peridotite that is an olivine pyroxene mantle in green. And we have a North Pacific crust that sits at the top of that. And in the middle, we have this metallic core. So the metallic core is very dense, and so it sits there cooling off, but it doesn't participate in the convection. The North Pacific crust is very buoyant and also getting cold, so it doesn't like to flow, and if it did flow, it would want to stay at the top. And so the main action is going to take place here in this layer of ilmenite-bearing cumulus that over time is going to heat up. Because of the radioactivity, and it's also denser. And so what's going to happen is that it's going to want to sit at the bottom of the mantle because it has a lot of iron in it. It's just iron and silicate minerals, not iron and metal, but iron and silicate minerals. But eventually it will heat up enough that it will become buoyant. And if it becomes buoyant, then it can rise towards the surface. It can rise through the overlying peridotite mantle. And so one of the important questions that I've been very interested in asking, and I think one of the most robust features of the structure of the moon that we know about, is the hemispheric asymmetry. And so the question that we were asking is, under what conditions, we've done this in a number of different studies, under what conditions can we generate a spherical harmonic degree 1, that is one big upwelling in the lunar mantle. So in the diagram on the right, the greenish kind of stuff, blue kind of stuff, in the middle of the moon surrounding the core are these ilmenite-bearing cumulus. And the picture here shows what would happen after about 300 million years of model time. After 300 million years of heating up, you can see the ilmenite cumulus eventually get hot enough, and you can see that on the right-hand side, you can see the temperatures, and you can see the ilmenite cumulus have gotten quite hot at this stage. And you can see that they rise to the surface in sort of one large upwelling. The other possibility is that they could rise to the surface in many smaller upwellings. And so that's the picture that you see at the bottom. What distinguishes the top and the bottom is that that everything is the same except the rheology. One of the things that we'll discover as we go along, and which Leif can tell you more about, is that rheology is a real key to understanding, the behavior that we see here. The top diagram would be a case where, so rheology. So I don't know if have you guys talked about rheology at all? A little bit, yeah. So solid state rheology involves creep, and creep is a thermally activated process. And so we describe the temperature dependence through an activation energy, which appears in an Arrhenius factor. That's that exponential term that you see here. And the top diagram is for the case where the activation energy is pretty low. And the bottom case is for a case where the activation energy is much higher, like twice as big. It's only twice as big, but it appears in an exponential. So that means, you kind of square the variation, by increasing it by a factor of 2. And one of the consequences is that as this IBC layer heats up at the base of the mantle, if the rheology is strongly temperature dependent, what happens is that the viscosity of that material becomes very low, and so that layer tends to convect internally and tends to lose heat, so it can't heat up as much. Whereas if the temperature dependence is low, like in the top diagram, one of the things you can see is that you don't have this internal convection going on, and so you can generate this sort of degree 1 hemispheric kind of instability. So I think one of the things we learned from this, I thought, was that yes, indeed, for at least reasonable parameters, you can generate degree 1 instabilities, but you really have to worry a lot about the rheology of the materials that you're dealing with. And you need to understand that very well if you want to draw firm conclusions about the evolution of the moon. Another important feature of the moon that is indicated here. One of the early observations of the moon was that there isn't any real global thrust faulting on the surface. I guess many of you have heard discussions of Mercury, and Mercury exhibits large thrust faults on the surface, globally distributed, but these appear not to be present on the moon. If they're not present on the moon, that would limit the amount of contraction of the moon that can occur. Thrust faults result from contraction of the interior, would limit the amount of contraction that the moon could undergo. That could have a couple of implications. One is that would limit either the thickness of the magma ocean that you had, the amount of volume change related to the magma ocean, or it could relate to how much temperature change you had in the interior. All right. So there's a paper here, there's a paper by Elkins, Canton, and Barkovici that showed up in 2014 that you can find that talks about the second 2 points here. It's sort of a modern treatment of magma ocean, perhaps magma expansion due to magma ocean solidification. They argue that magma ocean solidification would result in expansion of the interior of the moon, which would make sense because, when you freeze something, it expands, right? Water freezes in your pipes at home. You got a problem. It's going to break the pipes. Well, the same thing is true here. Magma freezes in the moon, it's going to expand and it's going to break the moon. And in the next image, I'll show you that from the Grail gravity field, and this is going to be really tiny if you're looking at it here, but sorry about that. I didn't realize that the screen is going to be so small. One of the features that the top diagram is the Grail-Bouguer gravity field. The middle is the gravity gradient. And the bottom is essentially the gravity gradient again, but it points out the existence of sort of linear features that show up in the gravity field that hadn't been known before the Grail gravity field. And I would really like a pointer now. I would really like a pointer that goes where I want it to go. There we go. Hopefully it is. So a feature like this one, for example, that's interesting. Yeah, a feature like that one, for example, has been interpreted as sort of dikes. I don't know what a dike is, right? That's been intruded into the lunar crust. And the interpretation of that in this paper by Jeff Andrews Hanna, which is referenced here, is that these reflect this early expansion of the moon due to the solidification of the magma ocean. What would happen after the magma ocean solidified? Well, after the magma ocean solidified, then the moon would cool off, right? And so one of the things that the model that I showed you in the last image, that is back here, would address would be how the volume of the moon would change as a function of time as it evolved in that simple model. And one of the things you can see is that two things are important. One is that so the volume is on the vertical axis, essentially time is on the horizontal axis in millions of years. And you can see that, well, if you took the limiting case of a mantle that had some uniform composition, that is uniform heating throughout, the moon would undergo large amounts of contraction, okay? And this would surely be enough to generate thrust faults, like you see on Mercury. Alternatively, if you localize the heat production down near the core mantle boundary, in this example that I showed you, you bury the heat much deeper, and it actually takes the heat much longer to get to the surface, to the bottom of the North Acidic crust, so that it can be conducted away. And so you can see that what happens initially here in the blue curves, you can see that in the blue curves the moon expands for a while because it's heating up, because we're generating heat faster than it can be carried away. And then finally it starts to cool off. And you can see you get with deeper heat sources, you get much lower, much smaller amounts of thermal contraction. And the other important factor here comes from the lunar crust. We said that the Grail people tell us that the lunar crust is pretty porous. And if you have a material that's porous, it can conducts heat much less well than material that's not porous, the same material that's not porous. And so the existence of a low porosity crust would reduce the ability of the North Acidic crust to transfer heat out of the mantle. And so it would sort of retain more heat in the interior. And so you would have slower contraction. And so again, whether this will ultimately work when we know more about the moon, but there's certainly a suggestion here that this would be one way to have less contraction due to cooling. Paleomagnetic field of the moon. Recent work by Ben Rice and others at MIT, I think, have demonstrated convincingly to most people that there was an early dynamo field that was generated in the presumably in the lunar core, most people would say. And in fact, the strength of the field decreased over time. Early on time is on the vertical axis. The green region there represents the region where the field intensity is really high. And then as you go forward in time, you can see that the field intensity is declining. And after about 3.2 million years of evolution, you can't find any convincing evidence that there is any more magnetic field in the inside of the moon. So the strength of the magnetic field and how long it lasted is important information. It's going to feed back on this question of what's the thermal structure, how fast is convection carrying heat out of the interior. And so this is a recent paper that talks about this. A number of papers have talked about this, but this is a recent one that I thought would be interesting to talk about because it's a paper by Alex Evans, who's here at Brown, and some of you may have for class right now. Again, you can download it and look at the details. There's really sort of more detail than I can show you. But so what Alex did here was that he looked at a simple case. We look at the two columns here. Let me get the two columns, this column and this column. He looked at the case where he had a chemically dense layer at the bottom, as we've been talking about. That's this region right here, if the pointer is working on the screen. It's not actually. Wow, that's weird. Huh?
Good.
It doesn't show up. Is it?
Mm-hmm.
Oh, wow, I just can't see it at all. Sorry, my eyes are bad. The case on the right is one of the things we learned about the moon recently, actually from Alberto Sol and Eric Horry, is there's more water in the moon than anybody ever thought, basically. You know, and maybe you guys can talk Alberto into coming here and telling you more about that sometime in the course of your class. But water has a huge effect on the rheology, as Leif can tell you. Has a huge effect. Orders of magnitude effect on the rheology. It can reduce the viscosity of olivine by, factors of 3 to 5 order. Yeah. So it's a huge effect. Okay. And so Alex explored the effect. What if this so-called IBC layer or creep layer had water in it? It wasn't dry. It was actually a wet rheology. And the conclusion is there would be a real big difference. And one of the big differences is that it would allow you to generate a magnetic field in the moon. The diagrams here that are called CMB, core mantle boundary heat flux, show you the heat flux out of the moon as a function of time. And they show you the cases where you have no water, you have a 200-kilometer water-enriched layer and a thicker water-enriched layer. The horizontal dashed red line here is the heat flux that you need to have a dynamo present in the core and generate a magnetic field. And you can see that that's pretty hard to do if you have no water there. But that if you put water in this so-called Illuminite cumulate layer, actually the mineralogy becomes weak enough that you can kind of lose lots of heat. You can have lots of heat transfer out of the core. Of course, this goes the opposite way to what I just told you. I told you earlier that I could generate the hemispheric asymmetry of the moon if convective heat transfer within this Illuminite cumulate layer wasn't too rapid. And the presence of the magnetic field seems to kind of push it in the other direction. And so what the balance of those two effects are is yet to be determined, basically. But maybe there's a constraint there. If not, there's at least something else that needs to go into the models that we're not thinking about yet. There's another recent paper. How are we doing on time? Not too bad. By Aaron Scheinberg, who is a student who actually worked with Maria Zuber at MIT. And one of the challenges about the lunar magnetic field is that it's extremely strong. The strength of a lunar magnetic field is, I don't know, the numbers probably don't mean very much, is like 70 microteslae. It's a lot stronger than the Earth's field. If you look at theories for convection in a metallic core, those theories would predict that you only had about one microtesla, not 70 microteslas. Sort of way down here, not way up here. And so the question is, so this kind of explains the timing, perhaps, but how can we possibly explain the strength of the lunar magnetic field? And so Scheinberg had the really interesting suggestion that one of the ways you could do that would be by having the magnetic field or some portion of the magnetic field actually be generated in what he calls a basal magma ocean. which would basically be this sort of Illuminite cumulate layer that sits at the bottom that's very rich in heat-producing elements that it could undergo melting. And that melt could be dense enough that it would actually stay down there, at least for a while. And so that melt and the convective motions of that melt, conductivity is apparently high enough that it could generate a magnetic field. And not only that, the magnetic field that you see at the surface of the moon is a very strong function of how far you are from the top of the region that's generating the field. The field falls off as 1 over the cube of the radius. And so, as you go from, as you go from a small core to this sort of larger region, the field that you see at the surface gets to be much larger. And you can at least explain some of the magnitude of the field of the moon by this kind of an effect. So maybe that ilmenite cumulate layer actually was convecting and helping to generate a magnetic field. Let's see. Why did I do this? I don't know why I did this. Oh, I know why I did this. Okay, so one of the things that we talked about was that that thorium, the element thorium, is kind of an indicator of this creep, these last magma ocean dregs. And one of the things that we recognized on the moon early on, back in the late 1990s, was that thorium is certainly concentrated in the area of the Mare basalt, but actually the thorium is actually more or less distributed radially, to some extent around the Imbrium impact basin. And so the suggestion is that a lot of the thorium that you're seeing at the surface here was actually excavated by the impact that generated the Imbrium impact basin. If so, that would imply that this creepy magma ocean residual material was at the base of the North Acidic crust, even at the time as early as the age of this impact basin. And on the left diagram at the left, you can see, looking at the ages of Mare basalt, you can see that impact basin comes before the Mare basalt, high titanium Mare basalt, which would have been generated by the melting of this material. And that kind of suggests that at least some of the Mare basalts were being generated by creep that stayed at a shallow level in the mantle. And that somehow that shallow level creep was concentrated on one side of the moon. And so one question you could ask is, well, how could you concentrate creep on one side of the moon? Well, one of the things you could do is you could say, well, if you did concentrate creep on one side of the moon, can you reproduce some of the features that we've already talked about? Can you reproduce Mare basalt volcanism? Can you produce convection in the interior that might generate a magnetic field? That's a really nice paper by Patrick de Neuville and others that was in JGR in 2013 here. Talks about that. They consider a model where they just sort of a priori place creep material, the heating due to creep material, at shallow depths in the mantle under the near side, and then ask about the evolution of the moon. Because the heat that you generate in the creep sort of eventually sort of spreads down by diffusion into the mantle, it also generates mantle convection. Heating from below would be more effective, but even heating from above will still generate convective overturn. And based on their work, they think that this could explain at least some important features that we've talked about. But I think that it still begs the question of how of how creep becomes concentrated on the near side very early in the evolution of the moon. If all of the creep went down and then it all came back up again in one area, then it's easy to understand why it would be there. But apparently, at least a fair amount of it is there, and it never went down. All right, that's kind of the basic picture. So one of the ideas that I've been kind of enthusiastic about is that based on a really simple model here, is that if you have a shallow, heavy layer in a spherical body, which is shown up here by the top diagram on the right, what will happen is that if the viscosity of that layer is very low, as we expect this creepy magma ocean residual material to be, it will become unstable, and eventually, even though the layer is quite thin, what will happen is that it will end up generating this kind of long wavelength instability, so that you can see that you can see from the arrows here that as this green stuff becomes heavier and cools off, you can see that it's all going down in one place. So you can imagine that if you had creep distributed at the top of the mantle, what you would be doing is you would be concentrating it over here in the region where all the flow is converging above this downwelling. There's a more recent study that looks at this, which actually looks at more sophisticated dynamical models. And again, this is a paper that's submitted for publication but not yet published. And again, the long and short of the story is that if you have a thin layer at the top of the mantle, and if the viscosity is low enough, and if it's dense but the viscosity is low enough, then you can create one downwelling. And it seems perfectly feasible that in that downwelling, what you could do is sort of concentrate the creep in one area of the mantle. And that would exist before the material that generated Mare basalt, ever reached a depth of 400 or 500 kilometers. So it would allow you to have lots of thorium around to be excavated before Mare basalt eruptions began. Right? That would be the argument there. And so I think we're kind of out of time. So do you want to continue on, or should we just wrap it up in 5 minutes? 5 minutes. Okay. So one of the really important questions is back to this question of how magma ocean works. And I'm gonna. Okay, couple questions. One of the questions is that we talk about this idea of overturn, where we have this heavy material sitting at the top, and one of the things that let's skip this for right now. Let's go and talk about how magma oceans would work. So this is a picture like the one I showed you earlier. That's just sort of a schematic picture of how we think a magma ocean might evolve with time. And the things different about this diagram is that the moon starts out initially molten. We start out generating these cumulus. But as we form cumulus, the way the cumulus are going to form is by crystals that are raining down on top of already deposited cumulus. And you could think of them as lots of mineral grains that have little spaces between them, or maybe not such little spaces. So those mineral grains could have relatively large amounts of melt trapped between them. Okay? And so if that trapped melt can't get out, then what's going to happen is that you can't do this sort of fractional crystallization where the residual liquid in the magma ocean becomes more and more iron-rich. To make that happen, you actually have to be able to get the melt out of the cumulus that are sort of sedimenting at the bottom of the magma ocean. We see the same process in sediments on the ocean floor, for example. When you deposit sediments, then over time they kind of compact, and the fluids that are contained kind of migrate out as the sediment column compacts. And it's should be the same thing in a magma ocean. And so what you need to do, so the melt is probably buoyant, but what you need to do is to be able to compact the crystals. You need to be able to squeeze them closer together. Okay? So you might imagine a bunch of spheres that you then squeeze until the space between the spheres diminishes and melt comes out. So ultimately, that's what we need to do to be able to generate this fractional crystallization. So the way that we might envision the evolution of the magma ocean of the moon is that before there's a north acidic crust, lots of cumulates would accumulate quickly. Like maybe if you calculate the radiation from the surface, for example, you could calculate that you can accumulate most of the cumulates in 10 to the 4th years, which is not very long, right? Once you have a north acidic crust, then the last dregs of the magma ocean, the last residual materials, because the north acidic crust is reducing the heat loss from the moon because it has to conduct to the crust, and it can't simply radiate from the surface at high temperatures. Then the magma ocean crystallizes much more slowly. The early phase of crystallization could leave lots of melt trapped in the cumulates. The later, and it could be only in the late stages on the 10 to the 8th kind of 100 million year timescales where you can actually extract that melt and where the cumulates have time to compact and allow that melt to get out. And so there are ways that we can assess that quantitatively in some time in some future seminar. Or if you want to ask questions later, we can talk more about how you might formulate models. But again, to give Leif a plug here, one of the important factors that's going to control how fast you can compact these cumulates are going to be the rheology of the cumulates. And that's going to go back again to the question of how much water is there, for example, because that's going to be controlling the solid state rheology. And so, you know, there are a lot of things that we could talk about. I hope I've given you here some kind of flavor for the kinds of questions and kinds of models that I think are useful for not necessarily answering questions about the moon, but in learning how to formulate new questions and how to think about observations that might be useful in either further refining those kinds of questions. So one of the observations that we sincerely definitely need are seismometers on the surface of the moon. So you have seismometers on the surface of the moon. All this is going to be in doubt. Yes. Unfortunately.
How many would you need? Like
I don't know. Some people think that on Mars you need only one. If you even had only one, that would be good. But I think it would be interesting to have a nice network. Yeah.
If we had an Apollo, except even broader parsec.
Oh, absolutely. Yeah.
Can you do the MG suite the next slide? Because it's going to be really interesting.
Oh, okay. We'll talk about the MG suite. So one thing about this compaction business, and so compaction and squeezing out the melt allows the olivine and pyroxene crystals that are retained at the bottom of the cumulate piles become progressively enriched in magnesium. All right. And one of the outstanding questions on the moon, in among all the samples that Apollo brought back to the Earth from the moon, were a group of rocks that are called the MG suite. I don't know if you've talked about that in this class. Is that a yes or no?
It would be coming up.
Okay. All right. Okay. So the MG suite. Let me see if I can get a pointer here. So if you look at the composition of samples in the moon, you can look at the magnesium content of the mafic minerals, and come on, I need a pointer. That's on the vertical axis in the diagram up on the right there, and the amount of calcium in the pelagic clays is on the horizontal axis. And so the vertical region here, darkly shaded, that are called fans, are the ferronorthicites. That's the north acidic crust. Basically, what you see there is that within the north acidic crust, you have a very pelagic phase that's very, very rich in calcium, but which covers a range of magnesium numbers. Okay. On the other hand, there's this group called the Mg suite that, first of all, has very high Mg numbers. That's its main characteristic, and there seems to be some correlation, perhaps, between Mg number and calcium content of the andesite.
That's from gut.
Huh?
Is that from the deep? Temperature and pressure.
Yeah, that's a good question. I mean, the diagram on the bottom shows you the ages, comes back to the question of ages of these different kinds of lunar rocks. And the little red box there shows the vertical axis is age, where age is decreasing downward. The horizontal axis is, you know, I won't call it that. It's no axis. It's just, but you can see that the magnesium-rich plutonic rocks are more or less contemporaneous with the fans, or the north acidic crust. But it has very high magnesium. So the question that's still outstanding, I think, is how these magnesium-rich cumulants were generated. And one of the ideas that actually Paul Hess, I think, was perhaps one of the first to propose, perhaps the first, was that one of the things you could do is that you could take these magnesium-rich cumulants that would exist right at the bottom of this cumulant pile that came from magma ocean solidification. And because they're relatively low in iron, they're buoyant. They would want to rise up towards the base. And if they rose and interacted with the creep layer, then what you could do is you could end up with rocks that are very typical of what I think of as the magnesium suite, which are very magnesium-rich rocks, but which also have the trace element characteristics of creep. And so this goes back to the issue of melt migration. And if you want to generate Mg-rich cumulants, one of the things that you need to do is that you need to be able to have compaction and the migration of melt out of the cumulants that are accumulating at the bottom, so that, you know, cumulants are not continuously or continuing to react with the melt from which they crystallize. You got to get that melt out of the way. So I don't know. That's my 5-minute shot on Mg suite.
Great.
There may be someone who's listening who knows a lot more about Mg suite than I do. I'm not a petrologist.
Okay, thank you very much, Mark. We'll now turn it over for questions, and Ariel Deutsch will run through a few questions that have been put in the chat box and collected here. Ariel?
All right, thanks, Mark. We have a lot of great questions from the class, so I'll try to get through them. The first is asking whether you could elaborate a little bit on the idea of a primitive moon layer and its evolution. For example, after gravitational overturn, what causes a primitive moon layer to end up sandwiched in between two cumulant layers?
Okay, well, we could quickly flip back. I didn't number slides. That would have been very useful in this kind of a setting. I can see that. But to go back to this slide, see if I can get a pointer here to show up. You can see that the thing that's called primitive moon in this slide, this is density. You can see that the density of the primitive moon is kind of intermediate between the early cumulants and the later cumulants. And so if you were to imagine that you were to simply rearrange the moon so that the density was increasing monotonically downward, what would happen is that this primitive moon would end up sandwiched between the very magnesium-rich cumulants and the magnesium poorer cumulants. All right.
Great, thank
Okay.
you. In the crystallization sequence, can you speak a little bit about the time scales for core formation and also the olivine crystallization?
Yeah, that's a good question. I guess that, you know, if the moon, depends on when the core formed. If we have a core dynamo, apparently existed from really early in the evolution of the moon. So the core, the metallic core, if that's where the dynamo is coming from, had to come out very early. Alternatively, if the dynamo is coming from a more illuminite as cumulate kind of layer region in the moon, then it could be perhaps a different story, I think. Then you would.
That was my question.
Yeah.
I was maybe curious about when you talk about this like really intense, vigorous flow.
Yeah.
How does that correlate with the formation of the core versus crystallization? And you know, because you were, you know,
Right. The core would form fast compared to any of these other things. You could imagine the core forming. If the moon were all liquid, you can imagine that the core would form because you would have droplets of iron that were kind of sinking through the silicate liquid mantle, right? And that process of sinking droplets, because the iron is so dense, would be really, really pretty fast.
You discussed the possible evolution of the overturned mantle structure. In the low activation case, where you produce a single large upwelling, what conditions determine where the single upwelling will occur?
Yeah. In the model that I showed you, the upwelling could occur anywhere. It could occur in any random position around the globe. There would be no preferred orientation, presumably.
So to piggyback on that question,
Yeah.
something I thought about when you brought it up was the position of the D double prime zones on Earth, how they're kind of very equatorial, maybe related to the spin of the Earth. I was wondering if that may potentially have an effect on, say, localization of some partially molten area on a certain side of the moon relative to the downwelling as well as rotation.
Yeah, it certainly could. There's a nice body of literature. One of the heat sources that we haven't talked about, I didn't try to talk about, was tidal heating. And so there are several recent papers that are really quite interesting, depending on how you think the moon may have formed. Tidal heating may have been very important early on. I don't know if Robin talked about that last week or not.
We actually had a question about tidal heating and whether tidal forces have any effect in concentrating radionuclides on near side versus far side.
Not that I can understand. Would be my simple answer.
So that was my question, and to elaborate on it more, like if you look at the distribution of moonquakes, right, and you think about tidal forces then causing some sort of compression, decompression, maybe you could think about distance between grains increasing, and you can get some sort of melt migration between the grains that would concentrate it on one side.
Yeah, you could. Yeah, I think that's the other thing that could concentrate it on the near side, which I didn't talk about, might be if the crust was thinner there. That might help too. But tidal forces, you know, if you just think about a uniformly spherical body, and you ask how are the tidal forces distributed, they're really equally distributed between the near side and the far side. You know, the moon actually, the field of the moon actually deforms into an ellipsoid.
But isn't that because there's both the rotation of the bodies and
yeah,
the
that's
moon
right.
orbiting the Earth? It's preferential on
that's
one
right.
side.
Yeah. I think most people think that the preferential one-sidedness, that the current side that faces the Earth was, you know, probably a consequence of its orbital evolution. I don't know. And density distribution.
Thinking a little bit about Robin's lecture last week, one of the things we discussed was how the moon is depleted in iron relative to Earth. So could you think a little bit about what this implies about the evolution of the moon's core and mantle relative to early Earth?
Well, one of the things it would suggest is that the core of the moon should be a certainly smaller fraction, volume fraction of the moon than it is of the Earth, which I think is definitely the case. I think that's sort of the main line of evidence. I guess you could say that one consequence of that could be that could be one of the reasons why the core dynamo in the moon probably doesn't seem like it would be robust enough to generate the magnetic field. If there were more iron in the moon, it could have a bigger core, and it could be big enough that you could actually generate a field of the strength that is observed, something closer to that.
So thinking a little bit about your experience with models, we have a couple of questions. The first is, can you elaborate on why solid cores can be excluded from models of magma ocean evolution? Is the heat in exchange between core and magma ocean insignificant?
No, the heat exchange between core and magma ocean is did you say core and magma ocean or core and?
I think the question was core and magma ocean.
Right. Okay. That's a good question, actually. I mean, I think it's worth thinking about that more. I have not heard anyone actually talk about that. Whether I think if the core, one of the things for sure is if the core is segregated from the magma ocean, from the liquid in the magma ocean, then the core is, to a very first approximation, right, it's going to start out at roughly the same temperature as the magma ocean. So the magma ocean is going to cool off convectively. And the magma down near the horizontal boundary is going to move up to the surface where it can lose faster. But the iron in the core is because it has atoms coming down there. So it can't lose convectively. So it's rising and losing heat. So I think that would kind of answer your question. So early people would be really important, particularly really early in the field that you would need strong core, and the magma ocean provides a very strong heat stock. Convective magma ocean would be very bigger.
Okay. Thinking a little bit about the convection process, what defines how many convection cells you have in the molten interior during the magma ocean formation?
Well, one example that you could think of would be Hadley cells in the Earth's atmosphere. And Hadley cells in the Earth's atmosphere are determined in two ways. One is sort of by the distribution of solar insolation on the surface, but it's also controlled by the thickness of the atmosphere. And so essentially the thickness of the magma ocean would be one factor that would control the size of convection cells. But like the atmosphere of the Earth, you might imagine that you have, like the Hadley cells, you might imagine that you have some sort of a large-scale convective circulation going on. It goes all the way from the bottom of the magma ocean to the top. But superimposed upon that, there are going to be lots of little buoyantly driven eddies or plumes that are helping to generate that larger circulation. That's what happens in the Earth's atmosphere. And so it's not either or. I mean, I think you have a whole multiple variety of scales that are present at the same time. It's not a very, perhaps not a very simple answer, but I think that would be the reality.
Is the lag time between overturn and the beginning of Mars volcanism consistent with our understanding of the mantle rheology?
Hmm. I think yes. I think the answer is, well, we don't understand the rheology of the lunar mantle.
Does it put any constraints on it?
Oh, it would. Yeah, absolutely. Yeah, it does. Going the other way, it certainly would. I think that as in these models, I mean, I think that the generation of Mars salts, having solid-state convection vigorous enough that you can generate a magnetic field would place an upper limit on what the viscosity of the lunar mantle could be.
Are the rheological properties consistent with near side and far side crustal thickness and members, or realistic favored rheologies?
I have a hard time relating crustal thickness right now to mantle rheology.
Actually, the question is in the model of a single convection cell producing, so you have a range of models, one of which will do that. Is that done with a favored rheology, or is it an in-member rheology? You know what I mean? It's like,
I think it was a pretty general rheology. Again, I would refer back to, there were a variety of images that I showed you, but, this one, for example, I mean, in this case, you have two different temperature dependencies of rheology, but that reflects in different viscosities as the temperature of the mantle evolves.
Neither of them are olivine or even close to olivine.
Well, they don't have an activation energy that defines olivine. I agree with that completely.
So olivine's like 530.
Right.
Correct. 300.
Correct. And that's a mystery for the rheologists, actually, because people who look at the evolution of the oceanic lithosphere in the Earth, sort of changing the subject here, but the seafloor on the Earth,
it's a planet.
Seafloor on the Earth subsides with age. That is, the seafloor is shallowest if you're at a mid-ocean ridge where plates are spreading apart. And as you go away from mid-ocean ridges, the seafloor subsides or sinks, and that's because of the cooling. The rocks in the upper mantle are becoming denser because they're losing heat. And in order to lose heat at rates that seem to be consistent with what's observed of the subsidence rate of the seafloor, you need, it's been stated that you need very low activation energies for the rheology of the Earth's upper mantle.
Thinking a little bit more about terrestrial analogs, if material is rising in many small plumes in the mantle, do we expect a lunar analog that may be similar to either large, low shear velocity provinces or ultra-low velocity zones?
Yep, I would think they would. I think that if the moon were behaving that way, that's exactly what you think might exist. But you have to remember that in thinking about that, you have to remember that maybe that's something that would have been present early in the evolution of the moon, and that once we get enough seismometers on the moon that we can really in detail map out the structure of the interior with confidence, you might not see that behavior. Even though you see that behavior on the Earth, because the Earth is so much bigger and mantle convection is so much more vigorous that that kind of structure is being sustained right now. But in the case of the moon, it could be that once you have this thick and orthostatic crust, you have pretty low heat flux, convection becomes pretty weak, and you just can't sustain that kind of structure.
Lastly, before we close, could you address whether there are any key observations of the moon that seem to be inconsistent with the magma ocean hypothesis?
Sorry, that was my question.
Well, what's your answer?
Well, I think that when we talk about hypotheses like this, people tend to present the very compelling evidence.
Yeah.
And so as someone who hasn't studied magma oceans in extreme detail, but did just read reviews of papers about all the planets and their magma oceans, it seems like for the moon, it's the most compelling case we have for a magma ocean, mainly because of the anorthositic crust, whereas on other planetary bodies, they're very easy faults to point out.
Right. Yeah. Yeah. So we have an anorthositic crust because the moon is relatively small. And so that affects the, so I don't think we would expect an anorthositic crust in a magma ocean on Mars, at least that's my understanding. And there's no evidence that there is any anorthositic crust that's been detected, I think. On the Earth, I think the Earth is vigorous enough that if there was an early magma ocean, that's kind of all been stirred up by plate tectonics and mantle convection.
But in principle, if we talk about a primary crust as being one which is impact generated, then there's no reason to suspect that the impact flux was similar at the moon and other planetary bodies that we wouldn't get something. It just might not be anorthositic. Predictably, it shouldn't be. And that raises a really important question, what does a kind of basaltic primary crust look like? What's the stability? How do you distinguish it from later secondary crusts and so on? It's a really important problem.
Yeah. So when you say that primary crust generated by impact, I think
impact heating, yes. It's Ross Taylor's basic classification some years ago.
So how big are the impacts that we're talking about? And what stage of the, if we're talking about impacts that are as large as the kind that Robin Knupp was talking about, right? Then
I think it's more like late stage accretion rather than, late heavy bombardment, something like that.
I see, okay, got you, okay. Well, I guess one of the if you looked at the moon, I guess you'd ask how you would generate the composition and heterogeneity of the basalts that you see, and the sort of age dependence of the compositions. On the Earth, I don't know. I guess on the Earth you'd. I guess on the Earth, that my first reaction is that all that stuff gets kind of wiped out by plate tectonics, but I'm always hopeful that some geochemists will come along here and find a smoking gun that is loaded.
Okay, thank you.
But one final comment, and the last image that I have for those of you who can look at images other than on the screen, is that understanding the lunar magma ocean is really important, because if you want to ask, is there an early magma ocean on Mars, for example? If you believe that there's an early magma ocean on the moon, then what would the consequences of that be for Mars? And so on Mars, I guess we don't expect an anorthositic crust. But what do we see on Mars that might be consistent? Well, we see hemispheric asymmetry. The figure on the left-hand side of this final image here is the Mars orbiter molar topography of Mars, and you all know, in the relatively young, low Martian plains and the much older, higher elevation highlands, and it really is a hemispheric kind of effect. And the other thing is that Lars Borg and others in a paper in 2003 looked at the mantle composition in isotopes that they would infer from SNC meteorites that are collected in Antarctica. So basically, understanding was that they basically do isotopic measurements on the meteorites, and then using those isotopic measurements, they ask and reasonable decay rates for the isotopes that are there. What would those samples have looked like when they were in the mantle? And there's a diagram on the right here that shows that if you look at all those SNC meteorites projected back to when they would have been samples in the mantle of Mars, you know, before they were melted and before they were erupted as salts that were then subsequently, you know, transported to the Earth in meteorites. Well, you can find isotopic evidence that would suggest that all of those inferred mantle compositions could lie on a mixing trend between the lunar mesa cumulus and the creep, and so to me that's very suggestive that, you know, they could have been generated in a magma ocean on Mars.
Okay, Mark, thank you very much. So this brings to an end this class, and I want to just emphasize that the video of the class will be posted online in the not too distant future, and we'll also put all of Mark's slides online as well, so you can pick up on the couple that bridge the gap between this final one about magma ocean on early Mars and what we talked about earlier. Next week, Maria Zuber will talk to us about the structure of the lunar crust, mantle, and core, a really nice complement to Mark's talk. And so if you have any additional questions for Marc, please email them to Marc or myself, and we can forward them and get them addressed as well. So thank you very much for tuning in, and we'll talk to you next week.